then there's a little namings here for these on table 32 or page 85. Alkyl halides, alcohols, ethers, amines, thiols, and it has sulfides. There are others, by the way. There are many, many others. And if you flip the page, you get aldehydes, ketones, carboxylic acid, etc. So you want to be able to configure your understanding of these. So if you have something like this, the first thing you're looking at is see the functional group that's a key point here, and it says, oh, this is an aldehyde. And I mean, I don't know the name of it, but I know how it is configured. So electronically, I know a few things right away. As soon as I know that, I know that there's electron withdrawal in this direction, right? So I know that that is kind of the business end of what's going to allow for reactions. How are we doing? Everybody okay so far? And so we understand that this aldehyde, by the way, is known as butyraldehyde because it has 1, 2, 3, 4 groups on it. The butyraldehyde functional, butyraldehyde molecule. So we also know that there are some issues related to this, and that we know that it has some qualities. For example, is there any hydrogen bonding here possible? Yes. Is it a hydrogen bond donor? No. The question, if you're asked on a quiz, is this a hydrogen bond donor? Is no. The reason is there any hydrogen which is attached to an electronegative element? There's no hydrogen attached to oxygen. There's no hydrogen attached to nitrogen and so on. But are there pairs of electrons here which could attract a hydrogen which is attached to another electronegative element? The answer is yes. You could have hydrogen bonding, for example, to an alcohol. So here would be the hydrogen bonding, right? Hydrogen bond acceptor, hydrogen bond donor. This is an alcohol, right? This is an aldehyde. Would they mix very nicely? Oh, absolutely. There's a hydrophobic end. There's a hydrophobic end. Here is a very polar end. So these interact very. So you would expect to say that these are very much soluble in each other or completely miscible, etc. Question?
No, I was trying to. So that was an alcohol attaching itself to that aldehyde.
So this is an alcohol, right?
Right.
And this is actually methanol, or methyl alcohol, and this is an aldehyde. So this is butyraldehyde, it happens to be. Now, or butanal would be another way to you think about it. Al signifies an aldehyde. Butanal. One butanal. This is 1, 2, 3, 4. We'll learn about how to do this later on. The consequence here is that you should be able to understand that there are intermolecular forces that you need to. I'll get to your question in a second. That intermolecular forces that you need to get comfortable with seeing them as you see a structure drawn. Yes?
That hydrogen will break off the alcohol, though, right?
It won't break off. It actually is going to be hydrogen bonded, and this end is delta minus, this end is delta minus, this end is delta plus. So they'll form a hydrogen bond here, but it won't. Yeah. To be very specific, it can come on and come off, come on and come off, okay, in the manner of picoseconds. But to say that this is going to make it permanently off is incorrect. It's just going to provide a linkage here between them as hydrogen bonding overlap occurs. So these things, because of this, are interacting very strongly with each other. Yeah, yes. Static is kind of a funny word there. It's being held between them. Yeah. So if you see this, now we can begin to talk a little bit about how these interactions make for additional exhibits. For example, you did an experiment lab in which you looked at miscibility and immiscibility. So you took some acetone, for example, and you put it into water, and you found it was completely miscible. Right? So here was the acetone. By the way, it's not a bad idea to start learning these things. So here's the acetone. Does it have a dipole moment because of its functional group? Yes. Here's the dipole moment, right? There's the positive side, there's the negative side, right? Does water have a dipole moment? Oh, of course it does. So here's the water dipole moment. And we have this positive end here, and it's attracted to this negative end, and lots of hydrogen bonding. Lots of hydrogen bonding. And there isn't that much hydrophobic issue here, although some. The water does not bind very strongly to this. In fact, it binds more strongly to the water than it does to this. And so here we have lots of hydrogen bonding, and since this is not particularly large, the water can envelop the whole acetone molecule, and you get complete miscibility. Still with me, ladies and gentlemen? So now we can take the idea that, wait a minute, we have something here that has hydrophobic parts, so we could take this, and here's some acetone, and now here is some benzene. Now benzene is a hydrocarbon which is aromatic, etc. It has no dipole moment to it because everything here is completely carbon hydrogen, and even though they're double bonds, they're all situated inside this configuration, which, by the way, is in resonance, right? So this thing is completely hydrophobic. Meaning fear of water, as in phobia, right? Or lipophilic, meaning lover of fat lipids. Huh? Lipophilic, yes. As in lover of fats. Hydrophilic, lover of water. Okay. So much for linguistics. Okay. The issue here is that this doesn't have any polar component. So, is it going to mix with the acetone?
No.
Does the acetone have non-polar components?
Oh yeah,
Let's draw them out a little bit, because sometimes we don't express them as nicely in the
Oh
picture.
yeah,
Everybody says,
acetone
"Oh,
is
we
both
don't think
polar
they
and
are."
non-polar.
Really, look at this. Will these things tend to interact? Absolutely. Is acetone completely miscible in benzene? Absolutely. Is acetone completely miscible in water? Absolutely. So acetone has a quality to it that allows it to mix both in water, because it has, I'll get to your question, it has a hydrophilic component to it, and allows it to mix in benzene because it has a lipophilic component to it. That's significant as a percentage of the volume of the structure. Yes?
So just to get a picture of this, would then the acetone surround the outside of the benzene ring,
Yes.
and then the acetone surrounding another benzene ring surround that, and that's how they get
Yes.
together?
Yes.
If you have acetone, benzene, and water,
Yes. And in fact, that's an excellent point. His question was, can you have acetone, benzene, and water? Yes. And there's a multi-million-dollar industry based upon that. Not with benzene, by the way, because you don't want to give people leukemia. Or acetone. But there are other things like acetone which allow you to mix water with a fine cream that you would want to put on your skin, but feels like Crisco when it's all by itself. Because you don't want to put Crisco on your skin, right? Just the lard. But here's the important thing. If you could put this in a water base that did not feel quote-unquote greasy, that felt good and wet, but when you put it on, it actually applies a layer of lipid, which then prevents water from evaporating quickly off your skin, and you call it lotion. And there's companies that put a little perfume in there too, which also is hydrophobic, and that enters the lotion. And you sell it for, I don't know, how much is lotion, real high quality lotion cost these days? Ooh. So, are there a few $1 million made every year? Yes, for exactly the reason that you have these things like acetone, which can mix water and a hydrophobic component.
Isn't that how soap works too?
1 second, what?
Is that how soap works too?
Not quite, but the concept in general is the same, but the details are different, and I'll show you. Yes?
So when you were talking before, you said acetone, but the functional group there is the ketone group, right?
That's correct.
And then when you added the CH3 on each side of the carbon, that's what made the acid.
No, that's what made it the ketone. So I'm going to answer your question first, then I'll get to your question, then I'll get to your question. I'll see if I can answer them all. But first, let's define, look at this. This is an aldehyde, right? On the left-hand side is the carbon, or the right-hand side would be kind of make a difference. What's on the other side? All aldehydes have only a hydrogen on one side and a carbon of some sort on the other side. That's an aldehyde. What's a ketone? Well, here's a ketone. This is a ketone.
So it's the oxygen and carbon connected to carbon, hydrogen, something?
Connected to two carbons on either side. You have that. This is a ketone. Okay? That's an aldehyde. By the way, it's interesting that you should recognize these differences because later on when you talk about the reactions, this is about 100 times more reactive than this towards all kinds of things. Okay? Which also many times says, these are much more toxic than this. We'll get into that a little bit later. Now, does that answer your question?
Yeah.
You had a question about
Soap.
soap. Okay, we're going to get to that right now. In 1 more minute. Yeah, another question.
Just one question. In ketone, for example, the functional group is carbonyl.
That's correct. And the aldehyde, what's the functional group? Say it. Carbonyl, but there are different types of carbonyls. You just talked about ketone, aldehyde. Is there another type? Carboxylic acid. That's correct. Is there another type? Ester. Congratulations. You've been reading the text.
But when you ask for functional group,
Here's what I would call.
If
If I say ketone, that means this structure, okay? You have to have R, C double bond O, R. If I ask for functional group, then you can have a choice that it would, as long as it includes a carbonyl, that's a carbonyl functional group, okay? But recognize that there's a functional group called an ester. Recognize that there's a functional group called the carboxylic acid.
The carbonyl is the oxygen and the carbon, right?
Period. And typically, the carbonyl is, honestly, mostly reserved for presentation with respect to aldehyde and ketone. A lot of little details. Anything else on, I'm going to get to the salts. Anything else on acids, carbonyls, ketones? Okay, so let's jump to soaps, which, by the way, brings us to that other multi-billion-dollar industry about one of them is not a soap that does not make your skin dry and crusty, etc. The one that's not a soap, right? I won't talk about what it is. Okay. So let's define soap. Soap has been around ever since somebody with a campfire and some ashes and some leftover fat from the meal they just had decided to boil the fat, throw the ashes into the boiling water, and discovered that, hey, this stuff would clean that crappy stuff off my hands. We'll call it soap. Believe that? I got another story. Let's start with something that exists in fatty tissue. And okay, there's stearic acid. Stearates. Where do they come from? Well, I'm going to get to that. They come from situations where fat cells accumulate fatty acids. So if we were to draw this thing out, see how I'm getting lazy, we can build it in 1, 2, 3, 4, 5, 6, 7. Anyway, I don't know. Was anybody counting today here, buddy? You get it. Okay? Is this something that can hydrogen bond?
Yeah,
I have controversy. I like that. Why do you say no?
I said yeah.
Oh, you said yes. Maybe I was. Yes, it can hydrogen bond. Because we have an oxygen with a hydrogen here, right? And we know over here we have a carbon with a double bonded oxygen, so we can have hydrogen bonding right over here. How about this long process down here? This is hydrophobic. Will this attach itself to water molecules? Absolutely. Will this attach itself to water molecules?
No, it's non-polar.
So, if you were to take some stearic acid that's pure and throw it onto water, it'll just sit there on the surface and float. You know, it's just not going to do much of anything. Now, what happens is, if we could make this a bit more intensely water soluble, then it would not just sit on the surface, but it would tend to mix more with the water. Because look, the majority of this structure is hydrophobic. So how could we make this a bit more water-loving, if you will? If we take this hydrogen off and leave it off, that gives us this resonance form here, right, with the carboxylic acid. And suppose we put a sodium ion there. So we have the sodium stearate. Okay? How do we get the sodium stearate? Well, if you think about this for a moment, if we had some sodium hydroxide, suppose we had some hydroxide ion here. Right? Sodium is simply a spectator ion, right? Hydroxide comes along. Still with me, ladies and gentlemen? Attracts to this hydrogen. So this hydrogen then gets pulled off. This pair of electrons goes to the oxygen. Now we have this stearate anion. So far, so good? This is charged, right? So if it's charged, it's attracting water like crazy. In fact, it is very intense at attracting the water, so much so that you get these shells of water molecules surrounding this. I'll get to your question in a second. But this, okay, does not mix well with the water because of entropy and thermodynamics at home, because all it can form is van der Waals type forces with the water, and those aren't very intense. So what happens is, someone made the comment earlier that it spreads out. If you put a very tiny amount of this in water, initially it sits on the surface, and this end goes up into the air, this goes into the water. But then what happens is, this end, if we look at it, starts to form a combination like this, and it's sloppy. And on this end is the negative charge, and the negative charge is sitting on the outside, and the inside here is lipophilic, and here's the outside. So here's the